There is a surface in the universe that has never been crossed in the outward direction. Not once. Not by anything. Not by matter, not by light, not by any signal of any kind, not in the entire 13.8 billion year history of the observable universe. Every piece of matter and every photon that has ever crossed this surface in the inward direction has stayed on the inward side permanently, adding to the object that the surface defines, contributing to the most extreme concentration of mass and curvature that physics permits. The surface is called an event horizon. The object it defines is a black hole, and the sentence that opens tonight's discussion is not a poetic description. It is a precise statement of what the laws of physics as we currently understand them require. Nothing that enters a black hole has ever come back out. Not ever. Not once. And the reason why has implications for the nature of time, the nature of space, the nature of information, and the nature of what physics is even capable of describing, that go far deeper than the striking simplicity of the sentence itself. Welcome to Dusk and Discovery. This one stays with you. Get comfortable, and let this be the night that black holes stop being something you know about and start being something you actually understand. Subscribe if you want more nights like this. Now, let us go in. The first thing to establish is what a black hole actually is, at the level of precision that allows the opening sentence to make sense, because the popular image of a black hole as a kind of cosmic drain or vacuum cleaner that sucks things in is wrong in a specific way that matters. A black hole does not suck. It does not pull anything that is not already on a trajectory toward it. A black hole sitting in empty space, with no matter nearby, does nothing to the space around it except curve it, and the curvature diminishes with distance in exactly the same way that the gravitational field of any other object diminishes with distance. If you replace the sun with a black hole of exactly the same mass, the Earth's orbit would not change at all. The planets would continue in their current orbits, the gravitational field at Earth's distance from the sun would be identical, and the only difference would be the complete absence of sunlight. A black hole does not reach out and grab things. It curves spacetime in its vicinity, and things that come close enough follow the curves of that spacetime in ways that lead inward rather than outward. The concept of an escape velocity is the clearest way to see what makes a black hole different from an ordinary gravitational object. Every massive body has an escape velocity, the minimum speed at which an object must be launched from the surface in order to escape to infinity without further propulsion. For Earth, the escape velocity is approximately 11.2 kilometers per second. For the Sun, it is approximately 617 kilometers per second. As you compress a given mass into a smaller and smaller volume, the surface gravity increases and the escape velocity from the surface increases. At some critical radius, the escape velocity reaches the speed of light. An object launched from the surface at the speed of light would be just barely unable to escape. An object launched at any speed less than light would definitely be unable to escape. And since nothing in the universe travels faster than light, nothing launched from this critical surface can escape. This critical radius is the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who derived the formula in 1916 from Einstein's equations of general relativity. The formula is elegant in its simplicity. The Schwarzschild radius is 2 times the gravitational constant times the mass of the object divided by the speed of light squared. For the Sun, this gives a Schwarzschild radius of approximately 3 kilometers. The Sun is currently about 700,000 kilometers in radius, far larger than its Schwarzschild radius, so it is not a black hole. But if you could compress all of the Sun's mass into a sphere 3 kilometers in radius, the escape velocity from the surface would equal the speed of light, and a black hole would form. The event horizon of a black hole is the spherical surface at the Schwarzschild radius. It is not a physical surface. There is no wall there, no membrane, no boundary that you could detect locally if you were crossing it. It is a mathematical surface defined by the geometry of spacetime, a surface whose defining property is that the escape velocity at that radius is exactly the speed of light. Inside the event horizon, the escape velocity exceeds the speed of light everywhere, which means that nothing can escape from any point inside it. Not because there is something blocking the path outward, but because the geometry of spacetime inside the event horizon is such that all future directed paths, all trajectories that go forward in time rather than backward, lead toward the center. Inside the event horizon, moving inward is not an option that can be avoided. It is the direction of time itself. This last point is the one that is hardest to convey, but most important to understand. The reason nothing can escape from inside a black hole is not that the gravitational force is too strong to overcome, in the conventional sense of a force being too strong. It is that the geometry of spacetime inside the event horizon is qualitatively different from the geometry outside. Outside the event horizon, spacetime has the normal structure in which you can move in any spatial direction, and time flows forward in a specific direction that is distinct from the spatial directions. Inside the event horizon, the roles of the radial direction and the time direction are exchanged, in a precise mathematical sense. What was the spatial radial direction outside the horizon becomes a time-like direction inside, which means that moving inward is not a choice made by matter inside the horizon, but the direction of increasing time. You cannot choose to move outward any more than you can choose to move backward in time. The future, for anything inside a black hole's event horizon, is always inward, always toward the center, always toward the singularity. This exchange of the spatial and temporal roles is one of the most counterintuitive features of black hole geometry, and it is what gives the opening sentence its specific force. Nothing that enters a black hole has ever come back out, not because nothing has been fast enough or energetic enough to escape, but because inside the event horizon, there is no such thing as a trajectory that goes outward. Outward is not a direction in time inside a black hole. It is a direction in the past, and the past is not somewhere you can go. To understand why Einstein's equations lead to this conclusion, you need some feel for what general relativity actually says about the relationship between mass, spacetime, and motion. General relativity is a theory of gravity, but it is not a theory of gravity as a force in the Newtonian sense. Newton described gravity as a force acting between masses at a distance, a force that accelerated objects toward each other in a way that could be precisely calculated given the masses and distances involved. This description works extraordinarily well for the conditions of everyday experience, including the motion of planets and satellites, and everything else in the solar system at the level of precision achievable before the 20th century. But it is not the deepest description. It is an approximation, accurate in weak gravitational fields and at velocities small compared to the speed of light, to a deeper theory that describes gravity very differently. In general relativity, gravity is not a force. It is a curvature of spacetime produced by the presence of mass and energy. Massive objects do not pull each other through a force transmitted across empty space. Instead, they distort the geometry of the spacetime in their vicinity, and other objects moving through that distorted spacetime follow the straightest possible paths available in the curved geometry, which are called geodesics. What looks like a gravitational force from the Newtonian perspective is, from the general relativistic perspective, the straightest possible path through curved spacetime. The Earth orbits the Sun not because the Sun is pulling it with a force, but because the Sun has curved the spacetime in its vicinity, and the Earth follows the straightest available path through that curved spacetime, which happens to be an ellipse. The curvature of spacetime is described by the Einstein field equations, a set of 10 coupled nonlinear partial differential equations that relate the geometry of spacetime, described by the metric tensor, to the distribution of mass and energy, described by the stress-energy tensor. These equations are among the most complex and beautiful in all of physics, and their solutions describe the geometry of spacetime in every possible configuration of mass and energy, from the gentle curvature near the Earth's surface to the extreme curvature near the event horizon of a black hole, to the global geometry of the expanding universe. Schwarzschild found the first exact solution of these equations for the case of a single non-rotating mass in otherwise empty spacetime, within weeks of Einstein publishing the theory in 1915, while he was serving on the Eastern Front in World War I. He sent the solution to Einstein from the front, and Einstein was reportedly astonished that an exact solution had been found so quickly for equations he considered nearly intractable. The Schwarzschild solution describes the geometry of spacetime around any spherically symmetric, non-rotating mass, including ordinary stars and planets. For the Sun, the deviations from flat spacetime predicted by the Schwarzschild solution are tiny, producing effects like the precession of Mercury's perihelion and the bending of light around the solar limb that were among the first observational confirmations of general relativity. For objects compressed to near or within their Schwarzschild radius, the deviations from flat spacetime become extreme, and the distinctive features of black hole geometry, the event horizon, the singularity, the exchange of spatial and temporal directions inside the horizon, emerge from the mathematics of the solution. What Schwarzschild's solution shows, when analyzed carefully, is that at the event horizon something qualitative changes in the structure of spacetime. The metric tensor, which encodes the geometry, develops what looks like a singularity at the Schwarzschild radius in Schwarzschild's original coordinates. For a long time, physicists debated whether this singularity was a real physical feature or a mathematical artifact of the coordinate system being used, in the same way that the coordinates on a map of the Earth become singular at the poles without there being anything physically special about the poles themselves. The resolution of this debate came through the work of several physicists in the 1950s and 1960s, including David Finkelstein and Martin Kruskal, who found coordinate systems in which the metric tensor is perfectly regular at the event horizon. In these coordinates, the event horizon is not a singularity. It is a perfectly smooth surface that an infalling observer can cross without experiencing anything locally dramatic. This is the aspect of black hole physics that is perhaps most surprising and most worth dwelling on. Crossing the event horizon of a sufficiently large black hole would not be locally detectable. An astronaut falling into a black hole of stellar mass would be killed long before reaching the event horizon by the tidal forces of the gravitational field, which would stretch the body along the radial direction and compress it perpendicular to that direction in a process physicists call spaghettification. But an astronaut falling into a supermassive black hole of billions of solar masses would experience tidal forces at the event horizon that are far weaker than the gravitational forces we experience on Earth's surface, weaker than the tidal forces of the Moon on the oceans. The event horizon of a supermassive black hole is so large, billions of kilometers in radius, that the curvature there is gentle enough that a human body or a spacecraft or an entire planet could cross it without any local indication that it had done so. The event horizon is not detectable locally. It is a global property of the spacetime geometry, a boundary defined by the causal structure of the universe as a whole, not by any local measurement. An infalling observer cannot know the moment of horizon crossing by any local experiment. The only way to know that the horizon has been crossed is to wait long enough to observe that light signals sent outward fail to escape, which is something that becomes apparent only after the crossing has already occurred. By the time you know you have crossed the horizon, it is too late to do anything about it. This feature of the event horizon as a locally undetectable but globally absolute boundary is one of the most philosophically interesting aspects of black hole physics. It means that the causal structure of the universe, the network of which events can influence which other events, extends beyond what any single observer can directly perceive. The event horizon is a feature of the universe's global causal structure that individual observers can be on one side of without knowing it. It is a reminder that the physics of the universe is not limited to what any single observer can measure, that the spacetime of general relativity is a global object with global properties that individual observers access only partially. The singularity at the center of the black hole is a different kind of feature from the event horizon, and it is one that represents not a solved problem but an open one. The singularity is a region of infinite density and infinite spacetime curvature predicted by the Schwarzschild solution, and more generally, by the singularity theorems proved by Roger Penrose in 1965. Penrose showed that once an event horizon forms, the formation of a singularity inside is inevitable, assuming the validity of classical general relativity and certain energy conditions on the matter involved. The singularity is not a point in space, but a moment in time, a future moment that everything inside the event horizon is inevitably falling toward, in the same sense that everything outside the event horizon is inevitably falling toward its own future. The singularity is where the trajectory of anything inside the black hole ends. But the singularity is not believed to be physically real in the sense of actually having infinite density and curvature. It is believed to be a signal that general relativity has broken down, that at the extreme densities and curvatures near the singularity, quantum effects become so important that a classical theory of spacetime is no longer adequate. The singularity is the mathematical representation of the edge of general relativity's domain of applicability, the place where the theory fails to give sensible predictions because it is being used outside the regime where it is valid. What actually happens at the center of a black hole, in the regime where quantum gravity is required, is not currently known. It is one of the central unsolved problems of theoretical physics, and its solution requires the development of a complete and consistent theory of quantum gravity that we do not yet have. The Penrose singularity theorems, for which Penrose shared the Nobel Prize in Physics in 2020, were a landmark in the mathematical understanding of black holes. They demonstrated that singularities are not merely possible outcomes of stellar collapse under special conditions, but are inevitable outcomes whenever an event horizon forms, regardless of the symmetry of the collapsing matter or the details of the collapse process. This was important because it showed that black holes are robust predictions of general relativity, not just solutions that exist under idealized conditions, but would not form in the messy reality of actual stellar collapse. The theorems also clarified something important about the causal structure of black holes. A singularity that is hidden inside an event horizon, as Penrose's results showed must exist whenever a black hole forms, cannot influence the external universe. The event horizon acts as a causal barrier in both directions. Nothing from inside can come out, but the singularity, whatever it actually is, also cannot send any influence outside. The external universe is permanently protected from the singularity by the event horizon. This is Penrose's cosmic censorship conjecture, which he proposed in 1969, and which has been the subject of extensive mathematical investigation since, but has not been rigorously proved. The conjecture says that in generic physical situations, singularities in general relativity are always hidden inside event horizons, that naked singularities, singularities without event horizons that could directly influence the external universe, do not form from regular initial conditions. If cosmic censorship holds, the universe outside a black hole is shielded from the singularity inside it, and the predictive power of physics outside black holes is preserved even though the physics at the singularity itself is unknown. The specific details of how a black hole forms are worth understanding because they illuminate what the event horizon is and how it comes into existence. In the most common route to stellar black hole formation, the iron core of a massive star, as we described in the stellar death video. accumulates mass until it exceeds the Chandrasekhar limit and collapses. The collapse happens in less than a second. The neutron degeneracy pressure that forms when the protons and electrons are forced together to form neutrons can halt the collapse if the core mass is below the maximum neutron star mass. But if the core mass exceeds this limit, the collapse continues past the neutron star configuration toward the black hole. As the collapse proceeds, the curvature of spacetime around the collapsing material increases, and at some point during the collapse, the event horizon forms. The event horizon does not form at the center and expand outward. It forms at a finite radius and then grows inward as more and more mass falls through it. Or more precisely, in the causal structure of the spacetime generated by the collapsing matter, there is a moment at which the spacetime first develops a region from which light cannot escape to infinity, and the boundary of that region is the event horizon. The formation of the event horizon is in this sense a global event in spacetime, not a local one. It is not something that happens at a specific point in space, but something that happens in the causal structure of the evolving geometry as a whole. Once the event horizon has formed, the remaining infalling material, the stellar envelope above the collapsing core, falls through it. From the perspective of a distant observer, this process appears to slow down as the infalling material approaches the horizon, due to the gravitational time dilation near the horizon. An observer watching from far away would see the infalling material appearing to freeze and fade at the horizon, never quite crossing it in the frame of the distant observer, though reddening and dimming to invisibility on a timescale of microseconds. In the frame of the infalling material itself, the crossing of the horizon is an event that happens in a finite and short proper time. The apparent freezing seen by the distant observer is a consequence of the way that photons emitted near the horizon take longer and longer to escape to the distant observer as the emitting material approaches the horizon, an effect of the curved spacetime, rather than a reflection of what the infalling material actually experiences. This distinction between what a distant observer sees and what an infalling observer experiences is one of the most important and most frequently confused aspects of black hole physics. A distant observer never sees anything cross the horizon, but the distant observer's inability to see the crossing does not mean the crossing does not occur. It means that the causal structure of spacetime near the horizon is such that photons emitted by infalling material after a certain point take infinite time to reach the distant observer, and photons emitted after the horizon crossing never reach the distant observer at all. The crossing occurs. The distant observer just cannot see it. The first experimental confirmation of a specific black hole's existence came not from watching something fall into a black hole, but from watching something orbit near one. The galactic center of the Milky Way harbors a supermassive black hole known as Sagittarius A star, with a mass of approximately 4 million solar masses. Over the course of several decades, astronomers at the Max Planck Institute for Extraterrestrial Physics and at the University of California, Los Angeles, tracked the motions of stars orbiting within a fraction of a light-year of the galactic center. The orbits of these stars, which move at speeds of up to 8,000 kilometers per second in tight ellipses with periods of a few years, can only be explained by the presence of an object with 4 million solar masses concentrated within the orbital radius of the closest stars. The most recent constraint from the orbit of a star called S2 places this mass within a sphere of roughly 125 light-seconds in radius, or about 37 million kilometers, far too small and too dark for any known collection of objects other than a black hole to occupy. The teams responsible for this work, led by Reinhard Genzel and Andrea Ghez, received the Nobel Prize in Physics in 2020, shared with Roger Penrose for his theoretical work on black hole singularities. The first direct image of a black hole, and more precisely of the shadow cast by the event horizon of a black hole on the surrounding hot plasma was published in April 2019 by the Event Horizon Telescope collaboration. The Event Horizon Telescope is not a single instrument, but a network of radio telescopes distributed across multiple continents, including facilities in Chile, Hawaii, Spain, the South Pole, Mexico, and Arizona, coordinated to function as a single Earth-sized telescope through a technique called very long baseline interferometry. By combining observations from all of these facilities simultaneously, the Event Horizon Telescope achieves an angular resolution sufficient to image structures at the scale of the event horizon of M87 central black hole, which has a mass of approximately 6.5 billion solar masses and is located roughly 53 million light-years from Earth. The image shows a bright ring of emission surrounding a dark central region. The bright ring is produced by light from the hot plasma surrounding the black hole, bent by the extreme gravity into a nearly circular pattern. The dark central region is the shadow of the event horizon, the region from which no light escapes. The size and shape of the shadow match the predictions of general relativity for a black hole of the observed mass to within the measurement uncertainties, providing the most direct confirmation to date that the objects predicted by general relativity and identified through stellar dynamics are indeed the objects described by the Schwarzschild and Kerr solutions of the Einstein field equations. The Kerr solution, derived by the New Zealand mathematician Roy Kerr in 1963, describes the geometry of spacetime around a rotating black hole. Real astrophysical black holes are not expected to be non-rotating, because the stars and gas clouds from which they form have angular momentum, and angular momentum is conserved during the collapse. A rotating black hole has a more complex geometry than a non-rotating Schwarzschild black hole, with features that have no Schwarzschild analog and that have profound implications for the behavior of matter and light in the vicinity of the horizon. The most important of these features is the ergosphere, a region outside the event horizon in which the rotation of the black hole drags spacetime itself into rotation so strongly that no object can remain stationary relative to distant stars, even if it has an arbitrarily powerful rocket engine. Inside the ergosphere, all objects are dragged in the direction of the black hole's rotation, but they can still escape to infinity because the ergosphere is outside the event horizon. The ergosphere is bounded by a surface called the static limit, outside of which objects can remain stationary, and the event horizon, inside of which nothing can escape. The region between the static limit and the event horizon is the ergosphere. The ergosphere has a remarkable property that was identified by the physicist Roger Penrose in 1971. It allows energy to be extracted from the rotation of the black hole. In the Penrose process, a particle entering the ergosphere can split into two particles, one of which falls through the event horizon and one of which escapes to infinity. If the splitting is arranged so that the infalling particle has negative energy in the reference frame of a distant observer, which is possible inside the ergosphere, the escaping particle carries away more energy than the original particle had. The energy comes from the rotational energy of the black hole. Each such process removes a small amount of angular momentum from the black hole, slowing its rotation. And in principle, the process could continue until the black hole has lost all its rotational energy and become a non-rotating Schwarzschild black hole. A related mechanism, the Blandford-Zienagic process, allows magnetic fields threading the ergosphere to extract rotational energy from the black hole in the form of electromagnetic energy, powering the relativistic jets that are observed in many active galactic nuclei and in gamma-ray burst sources. The jets from M87, which extend for thousands of light-years from the central black hole and were first observed by Heber Curtis in 1918, are believed to be powered by this mechanism. The images from the Event Horizon Telescope, in combination with polarimetric observations of the magnetic field structure near the event horizon, have provided observational support for the Blandford-Znajec mechanism as the power source for M87's jets. The black holes in the universe span an enormous range of masses, from stellar mass black holes of a few to tens of solar masses, formed in the depths of individual massive stars or in neutron star mergers, to supermassive black holes of millions to billions of solar masses at the centers of galaxies, to a hypothetical population of intermediate mass black holes of thousands to hundreds of thousands of solar masses, whose existence is suggested by some observations, but not yet firmly established. There is also a hypothetical class of primordial black holes, formed not from stellar collapse but from density fluctuations in the very early universe, which could have a wide range of masses from far below a solar mass to much above it. Whether primordial black holes exist, and if so what their mass spectrum is an open question with implications for the dark matter problem, since primordial black holes in certain mass ranges could constitute some or all of the dark matter. The gravitational wave observations from LIGO and Virgo have produced a census of stellar mass black holes that is already revealing surprises. The mass distribution of black holes detected in binary mergers shows a population in the range of roughly 5 to 80 solar masses, with a notable gap between roughly 2 and 5 solar masses, the mass range where neither neutron stars nor black holes are commonly observed. This gap, sometimes called the mass gap, may reflect a genuine absence of compact objects in this mass range, possibly related to the specific nuclear physics of supernovae and neutron star mergers, or it may reflect observational selection effects in the LIGO Virgo surveys. Some detections appear to involve objects in the mass gap, which are either the most massive neutron stars known or the least massive black holes known, and resolving their nature is one of the open questions in gravitational wave astronomy. More striking is the detection of black hole mergers involving objects that are too massive to have formed from the collapse of a single stellar core. The event GW190521, detected in May 2019, involved the merger of two black holes with masses of approximately 85 and 66 solar masses, producing a final black hole of approximately 142 solar masses. The more massive of the two progenitor black holes, at 85 solar masses, lies in the mass range where parent stability supernovae are expected to prevent the formation of black holes through normal stellar collapse, because stars in this mass range are predicted to be completely disrupted by pair instability rather than leaving a compact remnant. The existence of this black hole therefore either challenges the parent stability prediction or indicates that the black hole formed through a different route, such as the merger of two smaller black holes in a dense stellar environment like a globular cluster or a nuclear star cluster. The census of black holes from gravitational wave observations is already revealing a population that is more diverse and more puzzling than pre-detection theoretical predictions suggested. And as the detector sensitivity improves and the catalog of events grows, the picture will become richer still. The supermassive black holes at the centers of galaxies present a different set of questions. Their masses range from roughly 1 million solar masses for the smallest, found in dwarf galaxies, to approximately 40 billion solar masses for the most massive known, found in a galaxy called TUN 618. The relationship between the mass of the central black hole and the properties of the host galaxy, particularly the mass of the galaxy's stellar bulge and the velocity dispersion of its stars, is one of the tightest correlations in observational astronomy. The mass of the black hole is approximately a fraction of a percent of the mass of the bulge in almost every galaxy where both can be measured. This tight correlation, known as the m-sigma relation after the black hole mass m and the velocity dispersion sigma, implies that the growth of supermassive black holes and the growth of the stellar bulges of their host galaxies are linked in a specific way that they co-evolved rather than developing independently. The mechanism of this co-evolution is believed to involve feedback from the black hole's activity on the gas supply of the galaxy. When a supermassive black hole is actively accreting, the energy released by the accretion process, as matter falls toward the black hole and is heated to extreme temperatures, can drive powerful outflows of gas that sweep through the galaxy and suppress star formation. This feedback mechanism, in which the black hole regulates its own fuel supply by heating and ejecting the gas that would otherwise fall in and feed it and form new stars, is believed to be the reason why massive galaxies today are predominantly old, red, and star formation quenched. The black hole has essentially starved the galaxy of the cold gas needed for new star formation, maintaining the tight correlation between black hole mass and bulge mass by shutting off both processes simultaneously when the black hole has grown to the right fraction of the bulge mass. The accretion process that powers active supermassive black holes is the most efficient energy source in the known universe. When matter falls toward a black hole and is captured into an accretion disk, the gravitational energy released as the matter spirals inward through the disk can be converted to electromagnetic radiation, with an efficiency of up to approximately 42% of the rest mass energy for a maximally spinning Kerr black hole. This is an efficiency of mc² conversion that dwarfs nuclear fusion, which converts only about 0.7% of the rest mass of hydrogen to energy. A black hole accreting matter from a disk is roughly 60 times more efficient at converting mass to energy than a hydrogen bomb. The most luminous quasars in the universe, shining with luminosities thousands of times that of an entire galaxy, are powered by supermassive black holes accreting at rates of a few to tens of solar masses per year, with a conversion efficiency that makes them the brightest sustained objects in the observable universe. The radiation from accreting black holes, particularly the X-ray and gamma-ray emission from the innermost regions of the accretion disk, where temperatures reach billions of degrees, carries information about the geometry of spacetime at distances of just a few Schwarzschild radii from the event horizon. The study of this radiation, through a field called X-ray astronomy, has produced some of the strongest observational constraints on the properties of black holes, including measurements of the spin of stellar mass black holes in X-ray binary systems and of supermassive black holes in active galactic nuclei. The spectral shape of the iron K-alpha emission line, produced by fluorescence of iron atoms in the inner accretion disk, is distorted by the Doppler effect and gravitational redshift in ways that encode information about the radius of the innermost stable circular orbit, which in turn constrains the spin of the black hole. These measurements have shown that many black holes, both stellar mass and supermassive, are spinning rapidly, close to the maximum rate permitted by the Kerr solution. The innermost stable circular orbit is itself one of the distinctive features of black hole spacetime. Around a non-rotating Schwarzschild black hole, there are circular orbits for matter at all radii greater than 3 Schwarzschild radii, but below this radius no stable circular orbit exists. Matter that falls within 3 Schwarzschild radii spirals inward rapidly and crosses the event horizon. For a rotating Kerr black hole, the innermost stable circular orbit moves closer to the event horizon for orbits in the prograde direction, co-rotating with the black hole, and further away for orbits in the retrograde direction. For a maximally spinning Kerr black hole, the prograde innermost stable circular orbit approaches the event horizon itself. The position of the innermost stable circular orbit determines where the accretion disk terminates and matter begins its final plunge through the event horizon, and it is the dominant factor in the efficiency of energy release from the accretion process. Everything that has ever fallen past the innermost stable circular orbit of any black hole has continued inward, through the event horizon, to whatever fate awaits it at the singularity. The stellar matter from every black hole that has ever formed through stellar collapse, the gas and dust and smaller compact objects accreted over billions of years, the radiation absorbed from the surrounding environment, the gravitational wave energy deposited during binary mergers. All of it inside, all of it falling inward through the curved spacetime, all of it contributing to the mass of the black hole as measured from outside. And none of it, not one particle, not one photon, has ever come back out through the event horizon. The sentence is exact, the physics is clear, and the implications of that exactness, for information and for thermodynamics and for the foundations of physics itself, are what we are going to spend the rest of tonight carefully examining. The implications run deep, deeper than the physics of black holes individually, deeper than the astrophysics of accretion and jets and gravitational waves, deeper than the observational programs that have been confirming the existence and properties of black holes for the past several decades. The implications of the sentence "nothing that enters a black hole has ever come back out" reach all the way to the foundations of physics, to the question of what physics is capable of describing, and what it requires to be true about the universe at the most fundamental level. The specific implication we are going to spend most of tonight with is the one that Hawking identified in 1974, and that has not been fully resolved in the 50 years since. If nothing can come out of a black hole, what happens to the information about what went in? To understand why this question is so significant, you need to understand what physicists mean by information in this context, which is more specific than the ordinary meaning of the word. In physics, information refers to the quantum state of a system, the complete specification of every degree of freedom of every particle in the system, their positions, momenta, spins, and all other quantum numbers. Knowing the quantum state of a system at any given time, according to the laws of quantum mechanics, allows you to calculate the quantum state at any other time, past or future, with complete precision. This is the property called unitarity, and it is one of the most fundamental requirements of quantum mechanics. Quantum evolution is unitary, meaning that it is perfectly reversible in principle. Given the final state of a quantum system, you can always recover the initial state, and vice versa. Information is never created or destroyed. It is transformed and scrambled and redistributed, but the total amount of information in a closed quantum system is constant. Now consider what happens when you throw a book into a black hole. The book contains information, in the ordinary sense, words and ideas and arguments organized in a specific way. But from the perspective of physics, the book also contains quantum information, the complete quantum state of every atom in the book, including all the correlations between atoms that encode the specific structure of the text. According to unitarity, this quantum information cannot be destroyed. It must be preserved somewhere in the final state of the system, even if in a scrambled and unrecognizable form. But Hawking's calculation of 1974 showed that black holes emit radiation, and the radiation they emit is thermal. Thermal radiation is the maximum entropy form of radiation, the form that contains the minimum possible information for a given energy. A perfectly thermal spectrum of radiation carries no information about what produced it, in the same way that the infrared radiation from a warm wall carries no information about the molecular structure of the wall's material. The radiation carries energy but not specifics. If the black hole emits only thermal radiation throughout its evaporation and then vanishes, the information about everything that ever fell in, the complete quantum states of every particle, every atom, every book, every star, every galaxy that was ever absorbed is gone. It has been destroyed. And the destruction of quantum information violates unitarity, which is one of the most fundamental and well-tested principles of quantum mechanics. This is the black hole information paradox, and it is not a technical puzzle about the details of some exotic astrophysical object. It is a conflict between two of the most successful and most fundamental theories in all of physics. On one side is general relativity, which says that nothing comes out of a black hole, and that the interior is causally disconnected from the exterior. On the other side is quantum mechanics, which says that information is never destroyed and that the evolution of any closed quantum system is reversible. These two theories, general relativity and quantum mechanics, have both been tested to extraordinary precision in their respective domains. They have never contradicted each other directly in any experiment, because their domains of applicability have never significantly overlapped. Black hole evaporation is the regime where they overlap most directly, and in that regime they appear to be in direct contradiction. One of them, or possibly both of them, must be modified in the regime of quantum gravity. The person most responsible for bringing the information paradox into sharp focus was Jacob Bekenstein, a graduate student working under John Wheeler at Princeton in the early 1970s. Bekenstein was motivated by a simpler version of the information problem, the second law of thermodynamics applied to black holes. The second law says that the entropy of a closed system can never decrease. Entropy, loosely speaking, is a measure of how much information is hidden in the microscopic details of a system that is not accessible from macroscopic measurements. When you throw a book into a black hole, the entropy of the visible universe decreases by the amount of entropy associated with the book. The book is gone, and with it all the information it contained. If entropy can only increase in the observable universe, and if throwing things into a black hole decreases the observable entropy, then the second law of thermodynamics appears to be violated by the existence of black holes. Bekenstein's resolution of this problem was radical. He proposed that black holes themselves carry entropy, and that this entropy increases when matter falls in by enough to compensate for the decrease in entropy associated with the absorbed matter. He proposed that the entropy of a black hole is proportional to the area of its event horizon, not the volume of the black hole, which would be the natural measure if the entropy were counting the degrees of freedom of the material inside, but the area of its surface. The area of the event horizon increases when matter falls in, by exactly the amount required to satisfy the second law when combined with the decrease in entropy of the infalling matter. Bekenstein's generalized second law, which says that the total entropy, including the entropy of all ordinary matter and the entropy of all black holes as measured by their horizon areas, never decreases, is a precise and beautiful statement that resolves the thermodynamic paradox. But Bekenstein's proposal raised a question. If a black hole has entropy, then by the laws of thermodynamics it should also have a temperature, because the thermodynamic relationship between energy, entropy, and temperature requires all three to be consistently defined for any thermodynamic system. Bekenstein initially assigned a formal temperature to black holes, but treated it as an analogy rather than a literal temperature, because a literal temperature would imply that the black hole was in thermal equilibrium with radiation at that temperature, which would imply that the black hole was emitting radiation, which would imply that things were coming out of the black hole, which seemed impossible. Then Hawking did the calculation. In 1974, using a combination of general relativity and quantum field theory in curved spacetime, the discipline of studying how quantum fields behave in the background of a classical curved spacetime geometry, Hawking showed that black holes are not completely black. They emit thermal radiation at a temperature that is inversely proportional to their mass. The Hawking temperature for a black hole of mass m is equal to the reduced Planck constant times the speed of light cubed divided by 8 pi times the gravitational constant times the mass times the Boltzmann constant. For a stellar mass black hole of 10 solar masses, this gives a temperature of approximately 60 billionths of a degree above absolute zero, far below the temperature of the cosmic microwave background, and therefore undetectable in the current universe. For a primordial black hole of roughly 10 to the power of 11 kilograms, the Hawking temperature would be around 3 degrees Kelvin, comparable to the cosmic microwave background. For a black hole of the Planck mass, the fundamental quantum gravity mass scale, the Hawking temperature would be the Planck temperature, the hottest temperature that has a physical meaning in current theory. Hawking's calculation was received with astonishment and some skepticism when first presented. The result that black holes emit radiation seemed to contradict everything that had been established about the causal structure of black holes, the demonstration that the interior is causally disconnected from the exterior. The resolution lies in the mechanism of the radiation. Hawking radiation is not produced by anything inside the black hole. It is produced by quantum mechanical effects at the horizon itself, in the region of spacetime just outside the event horizon where the curvature is extreme, and the quantum vacuum is distorted by the gravitational field. The vacuum fluctuations of quantum fields near the horizon, the same zero-point fluctuations that are present everywhere in the universe, are affected by the black hole's gravity in a way that causes some of them to be amplified into real particles. The detailed mechanism involves the fact that the notion of particle is observer-dependent in curved spacetime, as we discussed in the context of the Unruh effect, and that an observer in the asymptotically flat spacetime far from the black hole sees a thermal spectrum of particles emerging from the region near the horizon, while an observer who is freely falling through the horizon sees nothing unusual. The key point for the information paradox is that Hawking's calculation showed the radiation to be exactly thermal, carrying no information about the state of the matter that formed the black hole or that has subsequently fallen in. The radiation is characterized entirely by the black hole's mass, charge, and angular momentum, the only properties of the black hole that are observable from outside, according to the no-hair theorem. The no-hair theorem, which was established through the work of Israel, Carter, Hawking, and others in the late 1960s and early 1970s, states that the external geometry of a black hole is completely determined by its mass, charge, and angular momentum. All other properties of the matter that form the black hole, its composition, its temperature, its entropy, its quantum state, are hidden behind the event horizon and inaccessible to external observers. Black holes have no hair, in the sense that they carry no external features beyond these three numbers. The combination of the no-hair theorem and the thermal character of Hawking radiation produces the information paradox in its sharpest form. The no-hair theorem says that all information about the infalling matter is lost behind the event horizon, accessible only to observers who fall in. The thermal character of Hawking radiation says that the radiation that eventually carries away all the black hole's mass carries no information about what formed the black hole. The black hole evaporates completely, and the final state, a thermal bath of particles at some temperature, carries no more information about the initial state than the temperature of a gas carries about the specific positions and velocities of its molecules before it came to thermal equilibrium. The initial state is forgotten. The information is destroyed. Unitarity is violated. Hawking himself, for many years, accepted this conclusion and argued that black hole evaporation represented a genuine violation of quantum mechanical unitarity, a modification of the rules of quantum mechanics required by the presence of gravity. This was a radical position, and most of the physics community was uncomfortable with it. The problem was that Hawking's calculation, while compelling, was a semi-classical calculation, treating the spacetime geometry as classical while treating the matter fields quantum mechanically. It was not a fully quantum gravitational calculation, and many physicists suspected that the information paradox would be resolved when a proper quantum theory of gravity was developed and the calculation could be done correctly. The most significant conceptual development in the information paradox came from the work of Don Page, a student of Hawking's, in 1993. Page analyzed the information content of the Hawking radiation over the course of the black hole's evaporation, using the tools of quantum information theory. He showed that if the evaporation process is unitary, meaning if information is preserved, The radiation must start carrying information about the initial state at some point before the black hole has completely evaporated. Specifically, he showed that if the total Hilbert space of the system, the space of all possible quantum states, is divided between the black hole and the radiation that has already been emitted, the entanglement entropy between the two subsystems must follow a specific curve, called the Page curve. The entanglement entropy starts at 0 when the black hole has just formed and no radiation has been emitted, increases as the radiation is emitted, and the entanglement between the black hole and the radiation grows, reaches a maximum at the Page time when roughly half the black hole's entropy has been radiated away, and then decreases back to 0 as the black hole finishes evaporating, and all the information has been encoded in the correlations of the radiation. Page's analysis showed that if Hawking's calculation were exactly correct and the radiation were exactly thermal throughout the evaporation, the entanglement entropy would not follow the Page curve. Instead of decreasing after the Page time, it would continue to increase monotonically, reaching a maximum at the end of evaporation that exceeds what is possible for a unitary process. This discrepancy between the Page curve required by unitarity and the monotonically increasing entanglement entropy predicted by Hawking's semi-classical calculation is the information paradox stated in its most precise quantitative form. One of these two results must be wrong. Either the radiation is not exactly thermal and contains information that Hawking's calculation missed, or the evaporation is not unitary and information is genuinely destroyed. The theoretical community was divided on this question for decades. On one side were those who, following Hawking, accepted the destruction of information as a necessary consequence of the combination of quantum mechanics and general relativity. On the other side were those who insisted that unitarity must be preserved, and that the resolution of the paradox would require showing that the Hawking radiation carries information in subtle correlations that the semi-classical calculation misses. The debate was not merely academic. It touched on the deepest questions about the nature of physical law. If information can be destroyed, then the laws of physics are not time-reversible at the fundamental level, which would be a radical departure from every other theory in physics. If information is preserved, then something in our understanding of black holes must be wrong, either the causal structure established by general relativity or the thermal character of Hawking radiation, or both. The resolution, or at least the current best approximation of a resolution, came from an unexpected direction: the study of quantum gravity in anti-de Sitter space through the AD-SCFT correspondence that we mentioned in the vacuum episode. Anti-de Sitter space is a spacetime with a specific negative curvature, different from the nearly flat spacetime of our universe, which has the mathematical property of having a well-defined boundary at spatial infinity. The AD-SCFT correspondence, proposed by Juan Maldacena in 1997, is a precise duality between a theory of quantum gravity in anti-de Sitter space and a quantum field theory without gravity living on the boundary of that space. In this duality, every process in the gravitational theory corresponds to a process in the boundary field theory, and vice versa. The boundary field theory in the AD-SCFT correspondence is an ordinary quantum field theory, and ordinary quantum field theories are unitary. Therefore, if the duality is correct, the gravitational theory in the interior must also be unitary, and black hole evaporation in anti-de Sitter space must preserve information. This was taken by many physicists as strong evidence that information is preserved in black hole evaporation more generally, even in the asymptotically flat spacetimes of the real universe, where the AD-SCFT duality does not directly apply. The argument is that if unitarity holds in one geometrically well-defined case of black hole evaporation, it probably holds in all cases, and the apparent information loss in Hawking's semi-classical calculation must be an artifact of the approximation rather than a real feature of the physics. The question of how exactly the information gets out remained open even after the ADS-CFT argument for its preservation. If the radiation is unitary and contains information, the information must be encoded in correlations between the individual Hawking photons that go far beyond what Hawking's thermal calculation shows. The individual Hawking photons, taken one at a time, look thermal. The correlations between them, across the entire sequence of photons emitted over the black hole's lifetime, carry the information. The correlations are real but extraordinarily subtle, and detecting them would require measuring the quantum state of every emitted photon simultaneously, an experiment of literally impossible complexity. The specific mechanism by which the information is encoded in the Hawking radiation became the subject of intense theoretical investigation in the decade following the ADS-CFT proposal. The key breakthrough came from understanding the role of quantum entanglement between the early and late radiation. In Hawking's original picture, each Hawking photon is entangled with a partner that falls into the black hole, and this entanglement is responsible for the thermal character of the radiation. As the black hole evaporates, more and more of the black hole's mass has been converted to radiation, and the radiation becomes increasingly entangled with itself. For the evaporation to be unitary, the late-time radiation must be entangled not just with the infalling partners inside the black hole, but also with the early-time radiation that has already escaped. This is the requirement imposed by the Page curve. The conflict between these two entanglement requirements was sharpened in 2012 by Almary, Maroff, Polchinski, and Sully, in a paper whose initials gave rise to the term AMPS firewall. They argued that the requirements of unitarity, no drama at the horizon for an infalling observer, and the validity of quantum field theory in the low curvature region near the horizon of a large black hole are mutually inconsistent. Specifically, they showed that if the late radiation is entangled with the early radiation as required by unitarity, then the entanglement between the Hawking radiation and its infalling partner is broken, and the event horizon becomes a region of high energy density, a firewall that would incinerate any infalling observer rather than allowing a smooth crossing as general relativity predicts. The firewall argument was controversial and generated an enormous amount of theoretical response. The controversy centers on what principle to sacrifice. If you sacrifice unitarity, information is destroyed and quantum mechanics is fundamentally modified. If you sacrifice the equivalence principle, infalling observers experience something dramatic at the horizon rather than a smooth crossing, and general relativity is fundamentally modified. If you sacrifice the validity of quantum field theory in the region near the horizon, then the semi-classical calculation on which all of the above reasoning rests is invalid, and the problem must be approached differently. None of these sacrifices is acceptable to those who hold the sacrificed principle sacred, and the debate has produced some of the most creative theoretical physics of the past decade. One of the most promising responses to the firewall paradox came from Maldacena and Susskind in their 2013 proposal that Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement are the same thing. The ER equals EPR proposal that we mentioned in the vacuum episode. The proposal is that two entangled particles are always connected by a microscopic wormhole, and that the entanglement between the Hawking radiation and the black hole interior is realized geometrically as a wormhole connecting the interior of the black hole to the exterior radiation. In this picture, the firewall does not form because the entanglement between early and late radiation does not sever the entanglement between late radiation and the interior. Instead, the late radiation is simultaneously entangled with the early radiation and connected to the interior through the wormhole, with the two types of entanglement being complementary aspects of the same geometric connection. The ER equals EPR proposal is beautiful and suggestive, but remains speculative. The specific mechanism by which the wormhole geometry encodes the information in the radiation, and the calculation that would reproduce the page curve from a specific model of the black hole's quantum geometry was not provided in the original proposal and remained elusive for several years. The breakthrough in making these ideas precise came in 2019 from a series of papers by Pennington and by Almeri, Mahajan, Maldacena, and Zhao, who showed that including the contribution of spacetime wormholes, called replica wormholes, in the calculation of the entanglement entropy of the Hawking radiation reproduces the page curve. The wormholes connect different copies of the spacetime in the calculation, in a mathematical technique related to the replica trick from quantum statistical mechanics, and their inclusion changes the long-time behavior of the entanglement entropy from the monotonically increasing Hawking result to the page curve required by unitarity. The calculation is in Euclidean quantum gravity, a formulation of quantum gravity in a space with imaginary time that is better behaved mathematically than the Lorentzian signature spacetime of ordinary physics, and it applies most rigorously in the context of the ADS-CFT correspondence. Whether the same calculation applies in the asymptotically flat spacetimes of the real universe is not fully established, but the result is taken as strong evidence that information is preserved in black hole evaporation, and that the page curve is the correct description of the entanglement entropy of the radiation. The specific mechanism of information scrambling and encoding that the calculation implies, while not fully spelled out, points toward the black hole horizon as a region of extraordinary quantum information processing, a place where information is received, scrambled at the maximum possible rate, and slowly returned to the universe in the correlations of the Hawking radiation. The concept of the scrambling time, the time required for the black hole to mix the quantum information of infalling matter with the quantum state of the entire black hole, has been analyzed through the lens of quantum chaos and quantum information theory. The black hole is believed to be a fast scrambler, scrambling information in the minimum possible time consistent with quantum mechanics, a time proportional to the logarithm of the number of degrees of freedom rather than the number itself. This is a remarkable property. Most quantum systems scramble information slowly, on timescales proportional to the number of degrees of freedom. Black holes are believed to scramble information as fast as physics allows. The theoretical argument for this, developed by Cecchino and Susskind, and elaborated by Hayden and Preskill, is that the scrambling time of a black hole is related to the thermalization time of the Hawking radiation, and that fast scrambling is required for the information to be returned in the early radiation in the specific way required by the page curve. Hayden and Preskill made a striking observation in 2007 that crystallized the operational meaning of the information paradox. They considered the following scenario. Alice throws a book into a black hole, then Bob, who has been collecting all the Hawking radiation emitted since the black hole formed, waits for the page time, and then collects a small additional amount of Hawking radiation. The question is whether Bob, with his collection of early radiation and the small additional sample, can in principle reconstruct the quantum state of the book. Hayden and Preskill showed that after the page time, the answer is yes, in principle. The information about the book is already largely encoded in the early radiation that Bob has collected, and the small additional sample after Alice throws the book in contains enough additional information to allow Bob to reconstruct the book's quantum state. The information does come out. It comes out scrambled beyond any practical ability to recover it, but it comes out in the correlations of the radiation, and a sufficiently capable quantum information processor could in principle extract it. The Hayden-Preskill result also highlights a profound asymmetry in the information paradox. The information about the book comes out of the black hole in the radiation, but not quickly. There is a delay of at least the page time, during which the information is processed by the black hole and gradually released in the correlations of the early radiation. The page time for a stellar mass black hole is enormously long, far longer than the current age of the universe. For a supermassive black hole, it is longer still. The information is not lost, but it is inaccessible on any practical timescale. The distinction between information being destroyed and information being encoded in correlations so subtle and so delayed that they are for all practical purposes unrecoverable is a fine one. And its philosophical significance depends on whether you think physics should be concerned with what is true in principle or what is accessible in practice. Most physicists believe physics should be concerned with what is true in principle. And on this criterion, the current theoretical consensus, informed by the ADS-CFT correspondence and the replica wormhole calculation, is that information is preserved in black hole evaporation and that unitarity holds. The information paradox, in its original stark form as a straightforward contradiction between general relativity and quantum mechanics, is considered by most theorists to be resolved in favor of quantum mechanics. The resolution required accepting that the event horizon is not as absolute a barrier as the causal structure of general relativity suggests, that quantum gravitational effects modify the geometry in ways that allow information to escape even when classical general relativity would forbid it, and that the spacetime inside a black hole is more tightly connected to the spacetime outside than the classical picture would indicate. But resolved is too strong a word. The specific mechanism, the precise quantum gravitational calculation that would show explicitly how the information is encoded in the Hawking radiation and how the replica wormholes connect to the physical process of evaporation, is not fully worked out. The entropy of a black hole, given by the Bekenstein-Hawking formula as 1/4 of the area of the event horizon in Planck units, is understood as a thermodynamic quantity, but the underlying microscopic degrees of freedom that the entropy is counting are not fully identified for black holes in the real universe, only for black holes in anti-de Sitter space, where the ADS-CFT correspondence provides a dual description. The firewall paradox has not been definitively resolved, and the question of whether an infalling observer experiences anything unusual at the horizon of a large black hole remains debated. What the theoretical developments of the past decade have established is a set of powerful and suggestive frameworks: the holographic principle, the ADS-CFT correspondence, the replica wormhole calculation, the ER equals EPR proposal, that collectively point toward a picture of quantum gravity in which spacetime geometry is not fundamental but emergent, in which the interior of a black hole is not causally disconnected from the exterior in the quantum gravitational sense, even if it is in the classical sense, and in which the relationship between entanglement and geometry is deep and constitutive rather than superficial and analogical. These frameworks have not yet been assembled into a complete theory of quantum gravity, and they may need substantial modification before they can be. But they represent genuine theoretical progress on one of the deepest problems in physics, and the problem itself, the question of what happens to information in a black hole, has driven more creative theoretical work in the past half-century than almost any other question in fundamental physics. The information paradox is also a reminder that the sentence "nothing that enters a black hole has ever come back out," while precise and correct as a statement of classical general relativity, is not the final word on what black holes are or what they do. Classical general relativity is an extraordinarily accurate theory in its domain of applicability. But its domain does not extend to the quantum regime, and the quantum regime is relevant for black hole evaporation and for the long-term fate of information in the universe. The final theory of quantum gravity, when it exists, will presumably reproduce the causal structure of general relativity in the appropriate limit, while modifying it at the quantum level in ways that preserve unitarity and allow information to escape from black holes over the evaporation timescale. The sentence will remain true classically, but the quantum story will be richer, stranger, and more connected. The richness and strangeness of the quantum story around black holes extends to the concept of black hole complementarity, proposed by Susskind, Thorlacius, and Uglum in 1993, as a way of reconciling the infalling observer's experience with the distant observer's experience without violating either general relativity or quantum mechanics. The proposal is that the information about infalling matter exists in two places simultaneously. It is encoded in the Hawking radiation as seen by the distant observer, and it is carried through the horizon by the infalling matter as seen by the infalling observer. This sounds like a violation of the principle that information cannot be copied, the no-cloning theorem of quantum mechanics. The resolution is that no single observer can access both copies. The distant observer who collects the Hawking radiation cannot then jump into the black hole to compare notes with the infalling observer, because by the time the distant observer has collected enough radiation to extract the information, the interior of the black hole has evolved to a state where the original infalling observer is no longer accessible. The two copies of the information are in causally disconnected regions, and no observer can ever verify that both copies exist. Black hole complementarity is a pragmatic resolution of the paradox, in the sense that it says the paradox is not a problem for any single observer, even though it seems paradoxical from the perspective of the universe as a whole. The two descriptions, information encoded in the Hawking radiation and information carried through the horizon, are complementary in the quantum mechanical sense of the word, much as position and momentum are complementary observables. You can use one description or the other, but not both simultaneously, and no contradiction arises as long as you are consistent about which observer's perspective you are using. The concept of complementarity applied to black holes raises deep questions about what it means for something to be real or objective in physics. If the same piece of information is encoded in two places that can never be compared, is there a fact of the matter about where the information actually is? If the description of the interior of a black hole depends on who is doing the describing, in the sense that different observers have different but internally consistent descriptions, what does it mean to say that there is a definite interior with definite properties? These questions lead directly into the foundations of quantum mechanics and the interpretation of the quantum state, and they are not resolved by black hole complementarity itself, but are sharpened by it. The Bekenstein-Hawking entropy formula, which assigns an entropy of 1/4 of the horizon area in Planck units to a black hole, is remarkable not just for its specific form, but for what it implies about the nature of entropy and information at the Planck scale. The formula says that the amount of information that can be stored inside a black hole is proportional not to the volume of the interior, which is what you would expect if information were carried by the constituent particles, but to the area of the surface. This is the holographic principle, which we have mentioned several times in these videos, now appearing from the specific perspective of black hole thermodynamics. The holographic principle says something profound about the nature of information in the universe. In ordinary physics, the information content of a region of space scales with the volume of the region, because information is carried by the particles inside the region, and the number of particles scales with the volume. The holographic principle says that the maximum information content of any region of space is bounded not by the volume, but by the area of the boundary of that region, measured in Planck units. This bound, the Bekenstein bound, is saturated by black holes. A black hole is, in this sense, the most information-dense object that physics permits in any given volume, and its information density is determined by its surface rather than its volume. The holographic principle implies that physics in 3 spatial dimensions can be described by a theory living on a 2-dimensional surface, that the 3-dimensional interior is in some sense a holographic projection of the 2-dimensional boundary. This is more than an analogy. In the context of the AD-SCFT correspondence, it is a precise mathematical duality between a 3-dimensional gravitational theory and a two-dimensional quantum field theory. The three-dimensional space of the gravitational theory is not fundamental. It is an emergent description, a convenient way of organizing the information that is fundamentally encoded in the two-dimensional boundary theory. Spacetime geometry, which general relativity treats as the fundamental arena in which physics takes place, is revealed by the holographic principle to be emergent, a derived concept arising from a deeper and more fundamental description in terms of quantum information. This emergence of spacetime from quantum information is one of the most radical and most exciting ideas in contemporary theoretical physics. It suggests that the question of what happens to information inside a black hole is not a question about what happens inside a region of space, but a question about how the quantum information of the boundary theory evolves. In the boundary theory, which is an ordinary quantum field theory without gravity, the evolution is unitary by definition. The information is always conserved. What we call the interior of the black hole in the gravitational description is a specific quantum state of the boundary theory, and the evaporation of the black hole corresponds to the thermalization and subsequent decoherence of that state in the boundary theory. The information is there all along, in the boundary theory. The puzzle of its apparent disappearance in the gravitational theory is an artifact of using the wrong description, a classical geometric description of what is fundamentally a quantum information theoretic process. If this picture is correct, then the sentence "nothing that enters a black hole has ever come back out" is true in the classical geometric description and false in the quantum information description. In the quantum information description, everything that enters the black hole is eventually encoded in the Hawking radiation, scrambled into correlations so subtle that no practical observer could ever recover them, but present nonetheless in the thermal bath of particles that the black hole leaves behind when it finishes evaporating. The event horizon is not an absolute barrier in the quantum gravitational sense. It is a region of intense scrambling, a place where quantum information is processed at the maximum possible rate and gradually redistributed into the outgoing radiation, hidden in correlations that span the entire history of the evaporation. This is the picture that the best current theoretical understanding of quantum gravity provides. It is incomplete and in some respects still tentative, but it is the direction in which the evidence and the theoretical arguments point, and it suggests that the most extreme objects in the universe, the objects from which nothing can escape in the classical sense, are not the endpoints of the story they appear to be from the outside. They are the most elaborate information processors that physics permits, taking in the quantum states of everything that falls through their horizons and returning it to the universe, profoundly transformed, in the faint glow of their Hawking radiation over timescales that make the age of the universe look like an instant. The most elaborate information processors that physics permits. That description, accurate as it is abstract in a way that makes it easy to lose the physical reality of what a black hole actually is for anything that approaches it. The information paradox and the holographic principle and the page curve are theoretical frameworks that operate at the level of quantum gravity, far from anything that could be directly experienced or observed. But black holes are also physical objects with specific geometries and specific effects on matter and light, effects that can be calculated precisely, and that produce phenomena that are in some cases among the most extreme that the laws of physics allow. The experience of falling into a black hole, if it could be had, would be unlike any other experience that physics permits, and working through what that experience would actually involve, hour by hour and kilometer by kilometer, reveals things about the geometry of spacetime that no other physical scenario brings into focus as clearly. The most important distinction for understanding the experience of falling into a black hole is the distinction between stellar mass black holes and supermassive black holes. The two have very different geometries at the event horizon, not in terms of the causal structure, which is the same for both, but in terms of the local curvature, and the local curvature determines whether approaching the event horizon is immediately lethal or deceptively gentle. A stellar mass black hole of 10 solar masses has an event horizon with a Schwarzschild radius of 30 kilometers. At this radius, the tidal forces, the difference in gravitational acceleration between the head and the feet of a body oriented radially, are enormous. Tidal forces scale as the mass of the black hole divided by the cube of the distance from the center. For a 10 solar mass black hole at the event horizon, the tidal acceleration across a human body is roughly 10 to the power of 12 times the gravitational acceleration at Earth's surface. This is not survivable by any biological organism or any material structure we know of. An astronaut falling toward a stellar mass black hole would be killed by tidal forces while still at a distance of thousands of kilometers from the event horizon, stretched along the radial direction and compressed perpendicular to it in the process physicists casually call spaghettification, which is an accurate description of what would happen to the body's geometry, even if it understates the violence of the process. A supermassive black hole of 1 billion solar masses has an event horizon with a Schwarzschild radius of approximately 3 billion kilometers, roughly 20 times the distance from the Sun to Earth. The tidal forces at the event horizon of this black hole are approximately 10 billion times smaller than at the event horizon of the 10 solar mass black hole, because the mass is 100 million times larger, but the horizon is 100 million times further from the center, and the tidal force scales as mass divided by distance cubed, giving a net reduction by a factor of roughly 10 billion. The tidal acceleration across a human body at the event horizon of this supermassive black hole is a tiny fraction of the gravitational acceleration at Earth's surface, a force so small that the astronaut would not notice it. The crossing of the event horizon of a sufficiently large black hole would be, locally, completely uneventful. This is the no-drama hypothesis, sometimes called the no-firewall hypothesis in the context of the firewall paradox we discussed in Part 2. For large black holes, the local geometry at the event horizon is very close to flat spacetime, and an infalling observer crosses the horizon without experiencing anything locally unusual. The only way to know that the horizon has been crossed is global. The fact that light signals sent outward after the crossing no longer escape to infinity. But this fact is not locally detectable. The photon you emit outward just after crossing the horizon moves outward at the speed of light in the local frame, and it takes a finite time before its failure to escape becomes apparent. The horizon is invisible to the observer crossing it. What would the infalling observer see during the descent? The exterior universe would appear dramatically distorted by gravitational lensing. The black hole's gravity bends light rays from background stars into complex patterns, concentrating them into a bright ring called the photon sphere at 1.5 Schwarzschild radii for a non-rotating black hole. Inside the photon sphere, photons can orbit the black hole in unstable circular orbits, producing the bright ring of emission visible in the event horizon telescope images. An infalling observer would see the background stars apparently shifting toward the direction opposite to the direction of fall, bunching into a ring around the sky, as the light from different directions is bent by the gravitational field. The sky above, in the direction of the black hole, would appear to narrow and darken, with only a small solid angle of the external universe visible through an increasingly narrow window as the observer approaches the horizon. After crossing the horizon, the infalling observer would continue to see the external universe through this narrowing window. But the window would continue to shrink, and the light from outside would be increasingly blue-shifted as it falls into the deepening gravitational well. The entire future history of the external universe would in principle be visible to the infalling observer, compressed into this shrinking window, because all photons emitted by the external universe after the horizon crossing will eventually fall through the horizon too, just later. The infalling observer can receive signals from the external universe indefinitely after the horizon crossing, at least in principle. What they cannot do is send signals back out. The singularity, toward which all infalling observers inside a Schwarzschild black hole inevitably move, is not a place in space. This is one of the most important and most counterintuitive features of black hole geometry, and it follows directly from the exchange of spatial and temporal roles inside the horizon that we described in Part 1. Outside the horizon, the singularity at the center of the black hole is in the spatial direction, toward the center. Inside the horizon, the singularity is in the future temporal direction. The singularity is not somewhere you are falling toward in the spatial sense. It is something you are approaching in the temporal sense. It is a moment in the future of everything inside the horizon, in the same way that tomorrow is in the future of everything alive today. This means that avoiding the singularity, once inside the horizon, is not a matter of finding the right direction to flee in. You cannot evade tomorrow by running in any direction. You cannot evade the singularity inside a black hole by accelerating in any direction, because all future-directed paths inside the horizon lead to the singularity. The maximum proper time before reaching the singularity, measured from the moment of crossing the horizon, is finite and proportional to the mass of the black hole. For a 10 solar mass black hole, the maximum proper time from the horizon to the singularity is roughly 60 microseconds. For a billion solar mass black hole, it is approximately 5 hours. For the most massive known black holes, tens of billions of solar masses, it is on the order of days. Larger black holes give more time inside, which is consistent with the intuition that the tidal forces at the horizon are weaker for larger black holes, and the spacetime inside is more nearly flat. The specific trajectory that maximizes the proper time before hitting the singularity is free fall, the trajectory of an observer falling in without any attempt to accelerate. Any rocket burn inside the horizon, any attempt to slow the fall or change direction, actually decreases the proper time before the singularity is reached. This is a consequence of the geometry. Inside the horizon, the radial direction is time-like, and the singularity is in the future of all radial directions. Accelerating radially outward inside the horizon is like trying to move backward in time, and the cost in proper time is real. The best strategy, if maximizing time inside is the goal, is to do nothing and fall freely. The singularity itself, when reached, is not understood. As we discussed in Part 1, the singularity is the point at which general relativity's predictions break down, the place where the curvature becomes infinite in the mathematical solution, and where quantum gravity effects must dominate. What actually happens to an infalling observer at the singularity is unknown, pending a theory of quantum gravity. Some theorists speculate that quantum gravity affects smooth out the singularity, replacing it with a region of finite but extreme curvature, where the observer's quantum state is dramatically transformed rather than destroyed. Others speculate that the observer's quantum information is reflected back and eventually encoded in the Hawking radiation, in a process mediated by the quantum geometry of the interior. These speculations are connected to the information paradox resolution we discussed in Part 2, but the specific mechanism is not yet understood. The geometry inside a rotating black hole, described by the Kerr solution, is more complex and more exotic than the Schwarzschild interior. The Kerr solution describes the spacetime of a rotating black hole of mass m and angular momentum j, and it has several features that have no analog in the non-rotating case. The most important of these for the interior geometry is the nature of the singularity. In the Schwarzschild black hole, the singularity is a space-like surface, a moment in time that all infalling observers inevitably reach. In the Kerr black hole, the singularity is a ring, a one-dimensional circle in the equatorial plane of the black hole's rotation, and it is time-like rather than space-like. The implications of this difference are profound. A time-like singularity, unlike a space-like one, is in the spatial direction rather than the temporal direction. This means that falling observers can in principle avoid a time-like singularity by steering around it, the same way they can avoid a wall by walking to one side. The Kerr ring singularity is in the equatorial plane, and an observer falling along the rotation axis would pass through the ring without hitting it. The mathematical structure of the Kerr solution near the ring singularity is also extraordinary. The spacetime near the ring singularity includes regions where the metric tensor has a negative value for the temporal component, producing what are called closed timelike curves, trajectories in spacetime that return to their own starting point in both space and time. Closed timelike curves would, if physically real, permit travel backward in time. The maximally extended Kerr spacetime, the complete mathematical solution of the Einstein field equations for a rotating black hole without any matter except the black hole itself, has a structure that can be visualized through a Penrose diagram. A Penrose diagram is a representation of spacetime in which the entire infinite spacetime is compressed into a finite diagram while preserving the causal structure, the pattern of which events can influence which other events. In a Penrose diagram, light travels at 45-degree angles, and the causal future of any event is the region of the diagram above and to the left and right of that event within a 45-degree cone. The Penrose diagram of the maximally extended Schwarzschild spacetime shows four regions: the exterior region from which we observe the black hole interior from which nothing can escape, a white hole region from which everything escapes and into which nothing can fall, and a second exterior region connected to the first only through the interior. The white hole is the time reverse of a black hole, a region from which matter is ejected rather than absorbed, and it exists in the complete mathematical solution even though it has no physical mechanism for formation, and is believed to be unphysical. The second exterior region is a second universe, completely disconnected from the first in the sense that nothing can travel from one to the other without passing through the interior, which requires faster-than-light travel. The connection between the two exterior regions is an Einstein-Rosen bridge, a wormhole, but a non-traversable one because the wormhole pinches off and closes before anything can pass through it. The Penrose diagram of the maximally extended Kerr spacetime is more complex, with an infinite tower of exterior regions connected by the wormhole-like passages through the ring singularity, and regions with closed time-like curves beyond the ring. If you fell through the ring singularity of a Kerr black hole without hitting the singularity itself, the mathematics suggests you would emerge into a different exterior region, a different universe, on the other side. The closed time-like curves near the ring would allow, in principle, travel backward in time. The multiple exterior regions connected by the Kerr geometry would form, in the complete mathematical solution, an infinite collection of universes connected by rotating black holes. These features of the maximally extended Kerr solution are mathematically precise and follow rigorously from the Einstein field equations. They are also almost certainly unphysical in the literal sense that they are not present in the black holes that actually exist in the universe. The reason is that the maximally extended Kerr solution describes the geometry of an eternal black hole, one that has existed for all time and will exist for all time, with no matter other than the black hole itself. Real black holes form from stellar collapse, and the interior geometry of a black hole formed by stellar collapse is not the maximally extended Kerr solution. The interior is determined by the history of the infalling matter and the exotic features of the Kerr solution, the multiple exterior regions, the ring singularity with its closed time-like curves, the connection to other universes, are artifacts of the idealized eternal solution that are not present in the realistic collapse solution. Specifically, the question of what the interior of a real stellar mass black hole looks like depends on what happens to the infalling stellar matter after the horizon forms. In the simplest models, the matter collapses to the singularity, and the interior geometry is dominated by the infalling matter rather than by the vacuum Kerr or Schwarzschild solution. The exotic features of the vacuum solutions are washed out by the presence of the collapsing matter, which modifies the geometry in ways that prevent the formation of the multiple exterior regions and the closed time-like curves. The real interior of a black hole is expected to be far more mundane than the mathematical solutions suggest, though still extreme enough to require quantum gravity for a complete description. There is a more subtle point about the interior of real black holes that is relevant to the information paradox and to the nature of black hole geometry. The interior of a black hole formed by stellar collapse grows over time as the black hole accretes matter. The horizon expands with each accreted mass, and the interior volume, in some sense that can be made precise in the quantum gravitational context, grows correspondingly. The interior of a black hole is not a static geometry. It is a dynamically evolving region that reflects the entire history of what has fallen in, and the quantum state of the interior encodes, in principle, the quantum states of everything that has ever passed through the horizon. This interior quantum state is the key object in the information paradox. According to the classical causal structure of general relativity, the interior is causally disconnected from the exterior, and the quantum state of the interior is inaccessible to external observers. According to the holographic principle and the AD-SCFT correspondence, the interior is not truly disconnected, and its quantum state is encoded in the boundary theory that also describes the exterior. The apparent disconnection is a feature of the classical description that is modified by quantum gravitational effects. The replica wormholes that reproduce the page curve connect the interior to the exterior in a quantum gravitational sense that has no classical analog, providing a channel through which information about the interior is gradually leaked to the exterior in the Hawking radiation. The physical picture that emerges from this theoretical framework is one in which the interior of a black hole is not a classical spacetime region with definite properties, but a quantum object whose description depends on the perspective of the observer and on the quantum gravitational effects that connect it to the exterior. For an infalling observer, the interior appears as a region of spacetime with a specific geometry, evolving toward the singularity in a finite proper time. For an external observer collecting the Hawking radiation, the interior appears as a quantum state of the radiation, gradually and subtly encoded in the correlations of the emitted particles. These two descriptions are complementary in the quantum mechanical sense, and the physical reality they describe is the same quantum gravitational object seen from different observational perspectives. The implications of this perspective for the experience of an infalling observer connect back to the firewall paradox we discussed in Part 2. If the Hawking radiation must be entangled with the early radiation in order to satisfy the page curve, and if this entanglement requires that the entanglement between the Hawking radiation and the interior is broken, then the infalling observer would encounter a firewall of high-energy radiation at the horizon rather than a smooth crossing. The firewall is the physical manifestation, in the infalling observer's experience, of the quantum informational requirement that the radiation carry information about the interior. If the radiation is entangled with the early radiation, it cannot also be smoothly entangled with the interior, and the resulting violation of the smooth vacuum state at the horizon produces the firewall. Most physicists find the firewall uncomfortable and expect it to be resolved by a more complete understanding of the quantum geometry of the horizon. The resolution may involve a modification of the concept of the infalling observer's experience in a way that has no classical analog, or it may involve a geometric structure at the horizon, such as the wormhole of the ER equals EPR proposal, that simultaneously satisfies the unitarity requirement and the no-drama requirement without contradiction. The specific form of the resolution is not yet known, and the firewall paradox remains one of the active frontiers of quantum gravity research. With all of these considerations, the causal structure of the Schwarzschild and Kerr interiors, the Penrose diagrams and their exotic implications, the information paradox and its potential resolutions. The firewall paradox and the complementarity principle have in common is that they are all pushing at the same boundary. They are all exploring what happens when the extreme conditions of black hole spacetime force quantum mechanics and general relativity to confront each other directly. The interior of a black hole is the natural laboratory for quantum gravity, the place where both theories are simultaneously relevant and where their current incompatibility is most acute. Every thought experiment about infalling observers and firewalls and closed time-like curves and the information paradox is, at its core, a probe of the nature of spacetime at the quantum level. The observable universe gives us indirect but increasingly precise information about black holes through their electromagnetic and gravitational wave signatures, as we discussed in parts 1 and 2. But the interior of a black hole is, by definition, permanently hidden from external observers. No direct observation of the interior will ever be possible from outside the horizon. The only way to observe the interior directly is to fall in, and nothing that has fallen in has ever communicated the result to the external universe. The interior of a black hole is the most observationally inaccessible region in physics, more inaccessible than the far side of the cosmic horizon, because the cosmic horizon is merely a limit of our light cone, while the event horizon is an absolute causal barrier. This inaccessibility does not mean the interior is unknowable. It means its properties must be inferred from theory rather than from direct observation, and the theoretical inference requires a theory of quantum gravity that we do not yet fully possess. The properties of the interior that we can infer from available theory include the causal structure, which is well understood from general relativity, the thermodynamic properties, which are well understood from black hole thermodynamics, and the quantum informational properties, which are increasingly understood from the holographic principle and the ADS-CFT correspondence. What we cannot yet fully infer is the dynamical description of what happens at the quantum gravitational level, as matter falls through the horizon and evolves toward the singularity, and whether the singularity is replaced by something finite and understandable in a complete quantum gravitational theory. The singularity replacement question has attracted several specific proposals. The most developed is loop quantum cosmology, an application of loop quantum gravity to the interior of black holes, which suggests that the singularity is replaced by a quantum bounce in which the infalling matter reaches a minimum volume and then re-expands, possibly into a new spacetime region. This new spacetime region would be, in the language of the Penrose diagram, a new universe, a region of spacetime causally connected to the interior of the black hole, but not to the exterior of the black hole. The Hawking radiation would carry information about what fell in, while the matter that fell in would be recycled into a new universe through the quantum bounce. This provides a form of information conservation that is distributed between two spacetime regions, the exterior and the new interior universe, rather than concentrated in a single region. Another proposal, motivated by string theory and the holographic principle, suggests that the singularity is replaced by a stringy geometry in which the fundamental constituents of spacetime, whatever they are in string theory, are in a maximally entangled quantum state that has no classical geometric description. In this proposal, the infalling matter reaches the strings at the center of the black hole and becomes absorbed into this maximally entangled state, its quantum information preserved, but in a form that has no local geometric description. The information would eventually be released to the exterior in the Hawking radiation through the quantum gravitational connections that the holographic principle provides. A third proposal, motivated by the work on fast scrambling and quantum chaos, suggests that the interior of a black hole is not a spacetime in the usual sense, but a highly entangled quantum state of the degrees of freedom at the horizon. In this proposal, which is related to the fuzzball conjecture of string theory, the horizon is not a smooth surface of empty spacetime, but a dense collection of fundamental strings and brains in a highly excited quantum state. There is no interior in the classical geometric sense. The entire black hole, including what would classically be the interior, is described by the quantum state of the horizon degrees of freedom. This is a radical modification of the classical picture, but it is consistent with the holographic principle, which suggests that all the physics of the interior can be encoded on the horizon, and with the fast scrambling property of black holes, which suggests that information is processed at the horizon rather than in the interior. These proposals are all speculative at the level of detailed mechanism, even though they are motivated by well-established theoretical frameworks. They share a recognition that the singularity of classical general relativity is not physically real and must be replaced by something finite in a complete quantum gravitational theory, and that the replacement has implications for the information paradox that are potentially resolvable in ways that preserve unitarity. The specific form of the resolution, the specific quantum gravitational description of what actually happens inside a black hole, awaits the development of a complete theory of quantum gravity and the calculation that would make the mechanism explicit. In the meantime, the black holes we observe are doing all of this, whatever it actually is, continuously and silently. The supermassive black hole at the center of the Milky Way, Sagittarius A star, with its 4 million solar masses and its horizon 30 million kilometers in diameter, is processing the quantum information of everything that has ever fallen into it over the history of the galaxy. And it is slowly, imperceptibly, leaking that information back into the universe in the faint trickle of Hawking radiation at a temperature of 10 to the power of -14 degrees above absolute zero. Colder than anything in the observable universe by many orders of magnitude. The information will not be substantially returned until the black hole has evaporated to a small fraction of its current mass, which will take approximately 10 to the power of 87 years. For now, the black hole holds the information, processes it, scrambles it at the maximum rate that physics permits, and waits. M87's central black hole, with its 6.5 billion solar masses, is more massive and more ancient and holds more information, and its evaporation timescale is roughly 10 to the power of 96 years. The information stored in it was deposited over billions of years of stellar and galactic evolution. Every star and gas cloud and smaller black hole that has ever been absorbed into the growing supermassive object at M87's heart. All of that information is inside the horizon, inaccessible to external observers by any classical means, and it will remain there for a duration that makes the entire current age of the universe look like the first microsecond after the Big Bang. The sentence remains true. Nothing that has entered these black holes has come back out. Nothing that has entered any black hole anywhere in the observable universe, in the 13.8 billion years since the Big Bang, has come back out. The event horizon has been crossed inward by more matter and radiation than we can currently estimate, by everything that was ever absorbed by every black hole that has ever formed, and the outward crossing has been exactly zero. Every galaxy in the universe has a supermassive black hole at its center, and every one of those black holes has been absorbing matter and radiation for billions of years, and not one particle has emerged from any of their horizons. The black holes are full, in the sense of containing all that has been absorbed, and they are patient, in the sense of processing it on timescales that are effectively infinite from the perspective of the stelliferous era. But the story does not end there, because the sentence is about what has come back out, not about what will come back out, and the physics says that eventually, given enough time, everything that went in will come back out in the form of Hawking radiation. The information will be returned. The ledger will be balanced. The unitarity that quantum mechanics requires will be satisfied. The price is time, vast amounts of it, time measured in numbers that have no common language description, and the coin in which the payment is made is so thoroughly scrambled and so impossibly correlated that no realistic observer could ever read the record of what went in from the record of what came out. But the physics says the record is there, in the thermal bath of particles that will be the black hole's legacy after it has finished evaporating, and the record is complete, and nothing that entered the black hole will have been truly lost. This is the strange and specific truth about the most extreme objects in the universe. They take everything in. They hold it for durations that exceed the age of the universe by factors that cannot be described in ordinary language. They process it at the maximum rate that quantum mechanics permits, and then, when they have finished, they return it, transformed beyond recognition, to the universe that produced them. They are not the endpoints of the story they appear to be from the outside. They are the most elaborate and patient of the universe's transformations, taking the information of everything that has ever crossed their horizons, and eventually, inexorably, returning it to the void from which it will continue on its longer journey. The ledger is balanced over infinite time. That sentence deserves to be the starting point for everything that follows tonight, because it contains within it one of the most remarkable facts that the study of black holes has produced. The universe keeps accounts. Not metaphorically, not in some vague karmic sense, but in the precise and literal sense that the laws of quantum mechanics require quantum information to be conserved, that the total information content of any closed quantum system is constant, and that black holes, the most extreme objects in the universe, the objects that appeared for half a century to be the one exception to this rule, are not actually exceptions at all. The ledger is balanced. Everything that goes in comes back out. The time required for the balance is incomprehensible. The form in which the information is returned is unreadable by any realistic observer. But the balance is there, written into the physics with the same certainty as the conservation of energy or the constancy of the speed of light. What this tells us about the nature of the universe is something that goes beyond black holes specifically, beyond astrophysics, beyond even the information paradox as a technical puzzle. It tells us something about what physics is and what it requires of reality. Physics, as a discipline, is built on the idea that the universe is lawful, that what happens next is determined by what is happening now according to rules that do not change and do not make exceptions. The conservation of quantum information, unitarity, is one of the deepest expressions of this lawfulness. It says that the past is encoded in the present with complete precision, and the present is encoded in the future with complete precision, that the laws of physics are perfectly time-reversible at the fundamental level, and that nothing is ever permanently lost in the sense of being truly erased from the universe's memory. Black holes, for 50 years, appeared to be the one place where this perfect lawfulness broke down. The event horizon appeared to be a boundary beyond which the encoding of the past in the present was severed, where information entered and did not return, where the universe's memory failed for anything that crossed inward. The apparent violation was so serious that Hawking, who discovered it, initially accepted it as a genuine modification of quantum mechanics required by the combination of gravity and quantum theory. For physicists who took this seriously, the information paradox was not merely a technical puzzle, but a sign that the deepest principle of physics, the conservation of information, failed in the presence of sufficiently strong gravity. The resolution, if the current theoretical consensus is correct, is that the failure is apparent rather than real. The information is conserved. The ledger is balanced. The event horizon is not an absolute barrier to the return of information, but a place where information is processed and scrambled and held for an extraordinarily long time before being returned in a form that, while in principle complete, is in practice unreadable. The universe's memory does not fail at the event horizon. It pauses for durations measured in exponents of exponents, and then resumes. Understanding why this is so, and why the apparent failure of information conservation took 50 years to resolve even in principle, requires sitting with a connection between gravity and thermodynamics that Bekenstein and Hawking revealed, and that, has proven to be one of the most productive theoretical discoveries of the 20th century. The connection is unexpected. Thermodynamics is a theory of heat and entropy and the direction of time, developed in the 19th century to describe the behavior of steam engines and gases and the flow of heat between objects at different temperatures. Gravity is a theory of the curvature of spacetime, developed in the 20th century to describe the motion of planets and the expansion of the universe and the formation of black holes. There is no obvious reason why these two theories should be related, and the fact that they are is one of the deepest hints about the nature of quantum gravity that we currently possess. The relationship was first noticed by Bekenstein in the form of the area theorem for black holes, proved by Hawking in 1971. The area theorem states that the area of the event horizon of a black hole can never decrease in any physical process, assuming the validity of general relativity and the weak energy condition, a condition that ordinary matter satisfies. This is a direct analog of the second law of thermodynamics, which states that the entropy of a closed system can never decrease. If the area of the horizon is the analog of entropy, then the area theorem is the gravitational analog of the second law, and black hole physics has a thermodynamics built into it by the structure of general relativity. Bekenstein made this analogy precise by proposing that the entropy of a black hole is proportional to the area of its horizon, and Hawking made it more precise still by calculating the constant of proportionality from first principles using quantum field theory. The result, the Bekenstein-Hawking entropy formula, is one of the most celebrated equations in theoretical physics. The entropy of a black hole is 1/4 of the area of the event horizon measured in Planck units, where the Planck unit of area is roughly 10 to the power of -70 square meters. For Sagittarius A star, with a horizon area of roughly 10 to the power of 23 square meters, the entropy is approximately 10 to the power of 91, in units where the Boltzmann constant is 1. This is an entropy so large that it exceeds the combined entropy of every star and every gas cloud, and every planet and every other form of matter in the observable universe. The black holes at the centers of galaxies are the dominant contributors to the entropy budget of the universe. The Bekenstein-Hawking entropy also encodes a specific answer to the question of how many degrees of freedom a black hole has, how many independent ways it can be internally configured that are consistent with the same external appearance. The entropy is the logarithm of the number of microstates, so a black hole of mass m has approximately e to the power of a over 4, where a is the horizon area in Planck units, distinct internal configurations. For a stellar mass black hole, this is a number so large that it has no common language description. For Sagittarius A star, it is e to the power of 10 to the power of 91. These are the number of distinct ways the quantum degrees of freedom of the black hole can be arranged while presenting the same external appearance to distant observers. The identification of the black hole entropy with the horizon area has a precise meaning in the AD-SCFT correspondence. The entropy of the black hole is equal to the entanglement entropy of the boundary quantum field theory across a specific surface that divides the boundary into two halves. The horizon area, measured in Planck units, counts the number of entangled pairs of degrees of freedom on the two sides of this division. Entropy in the gravitational theory is entanglement in the boundary quantum field theory. This identification is one of the most concrete realizations of the holographic principle, the idea that the three-dimensional physics of the gravitational interior is encoded in the two-dimensional physics of the boundary. The connection between gravity and thermodynamics goes even deeper than the entropy of black holes. In 1995, Ted Jacobson showed that the Einstein field equations, the equations that govern the curvature of spacetime in general relativity, can be derived from thermodynamics. Starting with the assumption that the entropy of any local Rindler horizon, a causal horizon associated with acceleration in flat spacetime, and related to the Unruh effect, is proportional to its area, and applying the first law of thermodynamics to this horizon, Jacobson derived the Einstein field equations as a thermodynamic equation of state. In this picture, general relativity is not a fundamental theory of spacetime geometry. It is a thermodynamic description of the collective behavior of the microscopic degrees of freedom that make up spacetime, in the same way that the ideal gas law is a thermodynamic description of the collective behavior of the microscopic molecules that make up a gas. Jacobson's derivation is remarkable because it suggests that the Einstein field equations are not fundamental laws but emergent descriptions, valid when the microscopic degrees of freedom of spacetime are in a state close to local thermal equilibrium. Just as the ideal gas law breaks down when the gas is far from equilibrium, the Einstein field equations might break down when the microscopic degrees of freedom of spacetime are far from equilibrium, which is precisely the regime near the singularities of black holes, where we know that general relativity fails. The thermodynamic interpretation of gravity provides a natural framework for understanding why the singularity is not physically real. Just as the equations of hydrodynamics break down when a fluid develops shock waves on scales comparable to the mean free path between molecules, the equations of general relativity break down when the spacetime degrees of freedom are driven far from equilibrium by the extreme compression near a singularity. Eric Verland extended Jacobson's work in a different direction with his proposal of entropic gravity, in which gravity is not a fundamental force, but an emergent entropic force arising from the tendency of physical systems to maximize entropy. In Verland's picture, the gravitational attraction between two masses arises from the information content of a holographic screen between them, and the force law follows from the change in the screen's entropy when the masses are displaced. This derivation, while controversial in its details, reproduces Newton's law of gravity and suggests that the familiar gravitational inverse square law is a thermodynamic consequence of the holographic principle, rather than a fundamental rule encoded in the structure of spacetime. Whether Verland's specific proposal is correct is not settled, and it has attracted both enthusiastic support and significant criticism from the theoretical physics community. But the direction it points, toward gravity as an emergent thermodynamic phenomenon rather than a fundamental force, is consistent with the broader picture emerging from the holographic principle and the AD-SCFT correspondence. In this emerging picture, spacetime and gravity are not the bedrock of physical reality but derived concepts, appearing as effective descriptions of a more fundamental quantum information theoretic reality at the accessible scales. The bedrock is quantum information. Spacetime is the language in which we describe the behavior of that information at the scales we can observe. Black holes are the places where this underlying quantum information reality becomes most visible, because they are the places where the thermodynamic properties of gravity are most extreme. The Bekenstein-Hawking entropy, the Hawking temperature, the area theorem, the information paradox, the firewall, the replica wormholes, all of these are aspects of the quantum information structure of gravity that become accessible to analysis when the spacetime curvature is extreme enough to make the thermodynamic properties of the horizon relevant. In mild gravity, the quantum information properties of spacetime are hidden behind the effective description of geometry. In extreme gravity, near the horizon of a black hole, they become dominant. This is why black holes have been so productive as theoretical laboratories for quantum gravity. They are not just interesting astrophysical objects. They are the regime where the thermodynamic structure of gravity is most directly accessible, where the entropy is concentrated in a measurable area, where the temperature has a calculable value, where the information paradox forces the confrontation between quantum mechanics and general relativity. Every theoretical insight about quantum gravity that has emerged from the study of black holes, the holographic principle, the AD-SCFT correspondence, the ER equals EPR proposal, the page curve calculation, has been driven by the necessity of understanding what the entropy and the temperature and the information content of the event horizon mean at the fundamental level. The holographic principle, which is perhaps the deepest of these insights, says something that is worth stating as clearly as possible. The maximum information content of any region of space is determined by the area of its boundary, not its volume. This is counterintuitive in the extreme. We live in what appears to be a three-dimensional world, and our intuition says that the information content of a region grows with its volume, because more volume means more space for more things to be in. But the holographic principle says this intuition is wrong at the fundamental level. The maximum information that can be stored in a region of space is determined by the two-dimensional surface that bounds it, measured in Planck units. The three-dimensional interior is not where the information really lives. It is a holographic projection of what is fundamentally two-dimensional. The practical implication of the holographic bound for ordinary experience is negligible. The holographic bound is so enormous, roughly 10 to the power of 66 bits per square meter of boundary area, that no physical system we have ever encountered or could plausibly construct comes anywhere near it. The human brain, with all its complexity, contains perhaps 10 to the power of 23 bits of information, a number that is far below the holographic bound for a brain-sized region. The holographic bound is not a constraint that limits anything in the ordinary world, but it is a constraint that limits the universe at its most fundamental level, and understanding why it exists and what enforces it is one of the central questions of quantum gravity. The answer that the AD-SCFT correspondence provides is that the holographic bound is enforced by the fact that the fundamental degrees of freedom of the universe are not in the three-dimensional interior, but on the two-dimensional boundary. The three-dimensional space of general relativity is not fundamental. It is an emergent description, valid when the boundary quantum system is in a state that is well described by a low-energy gravity theory. In states where the boundary system is highly excited, which corresponds to the presence of black holes or other concentrated matter in the gravitational description, the geometric description breaks down, and the more fundamental boundary description is needed. The temperature of a black hole, the Hawking temperature, connects to this picture in a specific way. Temperature in thermodynamics is a measure of the average energy per degree of freedom of a system in thermal equilibrium. The Hawking temperature of a black hole is the temperature at which the quantum vacuum near the horizon radiates, as measured by a distant observer. In the holographic picture, this temperature corresponds to the temperature of the boundary quantum field theory in the state dual to the black hole. The relationship between the black hole's mass and its temperature, the Hawking temperature being inversely proportional to the mass, is the gravitational analog of the relationship between the energy and temperature of any thermal system. The laws of black hole thermodynamics, the complete set of relationships between the mass, area, temperature, and entropy of black holes, are perfect analogs of the laws of thermodynamics, with the mass playing the role of energy, the area playing the role of entropy, the Hawking temperature playing the role of temperature, and the angular momentum and charge playing the roles of other thermodynamic variables. The zeroth law says that the surface gravity of a stationary black hole is constant over the horizon, analogous to the statement that the temperature of a system in thermal equilibrium is uniform. The first law says that small changes in the mass, area, angular momentum, and charge of a black hole satisfy a relationship that is the exact analog of the first law of thermodynamics relating energy, entropy, temperature, and other thermodynamic variables. The second law is the area theorem, stating that the total horizon area never decreases. The third law says that the surface gravity of a black hole cannot be reduced to zero in a finite number of operations, analogous to the statement that absolute zero temperature cannot be reached in a finite number of steps. These four laws were originally presented as formal analogues of the thermodynamic laws, interesting formal similarities that might or might not have a deep physical significance. Hawking's calculation of the black hole temperature showed that they have a deep physical significance. The analogy is not merely formal. Black holes are thermodynamic systems, with a real temperature and a real entropy, obeying the real laws of thermodynamics. The consequence is that black hole physics is inseparable from thermodynamics, that understanding black holes requires understanding entropy at the fundamental level, and that the entropy of the event horizon is not a convenient bookkeeping device, but a reflection of real microscopic degrees of freedom in the quantum gravitational description. What are those microscopic degrees of freedom? This is the question that drives much of the current research in quantum gravity. In string theory, the degrees of freedom are strings and branes in specific configurations, and the calculation of the entropy from counting those configurations has been carried out for specific black holes in anti-de Sitter space, reproducing the Bekenstein-Hawking formula. In loop quantum gravity, the degrees of freedom are the spin network states that define the quantum geometry of the horizon, and the counting of those states also reproduces the Bekenstein-Hawking formula up to a numerical factor that depends on the choice of a parameter in the theory. Neither calculation has been carried out for the black holes that actually exist in the universe. In asymptotically flat spacetime, without the mathematical simplifications of anti-de Sitter space, or the specific symmetries of the black holes used in the string theory calculations. The fact that two very different approaches to quantum gravity, string theory and loop quantum gravity, both reproduce the Bekenstein-Hawking entropy formula from the counting of microscopic states is encouraging. It suggests that the formula is robust, that it reflects a genuine property of quantum gravity that will be present in any correct theory, and that the counting of degrees of freedom at the horizon is a real and meaningful calculation, rather than an artifact of a particular theoretical framework. What the correct theory of quantum gravity actually describes those degrees of freedom as being, their physical nature and their dynamics, is not yet known. The deepest question that black holes force us to confront is one that has been implicit in everything we have discussed tonight, but that has not yet been stated directly. The question is, what is space? Not what is in space, not how space curves in the presence of mass, but what space itself is at the most fundamental level. The holographic principle and the ADS-CFT correspondence together suggest that the answer is, space is not fundamental. Space is an emergent description of a quantum information structure that is itself not spatial. The geometry of three-dimensional space is a derived concept that appears when you describe certain quantum systems in a particular way, and it dissolves, along with its content of matter and fields and black holes, into the underlying quantum information when you ask questions at the fundamental level. This is a conclusion that sits at the edge of what current theoretical physics can rigorously establish. The evidence for it, from the holographic principle, from the ADS-CFT correspondence, from the replica wormhole calculation, from Jacobson's derivation of the Einstein equations from thermodynamics, is strong and convergent. But a complete and explicit theory in which space emerges from quantum information, in which the three-dimensional geometry of the universe we observe is derived from a more fundamental description, does not yet exist. What exists is a collection of hints, powerful and consistent and mutually reinforcing, that point in this direction. The development of the complete theory, the explicit construction of the quantum information substrate from which spacetime emerges, is one of the central unsolved problems of theoretical physics, and may be the most important scientific question of the current era. Black holes are the objects that make this question most acute, because they are the objects where the tension between the geometric description of general relativity and the quantum information description of quantum mechanics is most severe, and where the hints about the deeper description are most clear. The event horizon is where the two descriptions diverge most dramatically. In the geometric description, the event horizon is an absolute boundary between the outside and the inside, a surface beyond which no information can travel. In the quantum information description, the event horizon is a region of intense scrambling and processing, connected to the exterior by quantum entanglement and wormholes in a way that eventually returns all information to the outside world. These two descriptions are not in conflict in any single observable, because the quantum gravitational effects that allow information to escape are so subtle and so delayed that they are undetectable on any observational timescale. But they point in fundamentally different directions about the nature of spacetime and causality, and the true description, when it is eventually established, will require one of these pictures to be the fundamental one and the other to be the approximation. The current theoretical evidence strongly favors the quantum information description as the fundamental one. The geometric description, with its absolute event horizons and its singularities, is an excellent approximation in regimes where quantum gravity is negligible. In the long run, on the timescales of Hawking evaporation, it is the approximation that fails. The universe, at its most fundamental level, appears to be a quantum information system, and the geometric spacetime that we experience is the particular way that quantum information manifests itself when it is organized in a low entropy, low curvature configuration like the one that has prevailed since the Big Bang. Sitting with this conclusion, in the context of everything that black holes have taught us, produces a specific kind of vertigo that is different from the ordinary vertigo of large numbers and vast timescales. It is the vertigo of realizing that the most familiar and seemingly indubitable thing in experience, the existence of a spatial world with locations and distances and the specific quality of being somewhere, is not the bedrock of physical reality but a derived phenomenon, a particular way that quantum information organizes itself under certain conditions. The chair you are sitting in is real. The room is real. The night outside is real. But these things are real in the way that the temperature of a gas is real. As an emergent description of an underlying reality that does not itself have temperature, that is not itself at a specific temperature. The temperature is genuinely there, measurable and consequential and lawful, and it is not fundamental. Beneath it is the kinetic energy of individual molecules, and beneath that is the quantum mechanics of atomic interactions. And the question of what is beneath that is the question that black holes are helping us answer. What is beneath that, if the holographic principle is correct, is quantum information, entanglement, the correlations between quantum degrees of freedom that do not themselves live in space but that, when organized in certain ways, give rise to the appearance of space and matter and fields, and the specific geometry that general relativity describes. The quantum information is the bedrock. The space that seems so obviously real, so obviously the container of all things, is the hologram. Black holes are the points in the hologram, where the holographic nature becomes most visible. At the event horizon, where the geometry of spacetime is extreme enough to produce a finite temperature and a calculable entropy, where the information paradox forces the quantum and the geometric into direct conflict, where the replica wormholes and the page curve reveal the quantum gravitational connections that classical geometry ignores, the holographic nature of the universe is closest to the surface. The black hole is not just an extreme astrophysical object. It is a window into the structure of reality at the deepest level. This is what the sentence "nothing that enters a black hole has ever come back out" is really pointing at. Not just the causal structure of the event horizon, not just the thermodynamics of Hawking radiation, not just the information paradox in its technical formulation, but the underlying question of what spacetime is, and what information is, and what the relationship between them tells us about the nature of physical reality. The sentence is a clue. The causal structure of the event horizon is a clue. The temperature and entropy of the horizon are clues. The page curve is a clue. All of them are pointing at something that we are still in the process of understanding, a deeper structure of reality in which the apparent impossibility of anything coming back out of a black hole is resolved by a more fundamental description in which the interior and the exterior are more tightly connected than classical geometry suggests. We do not yet fully understand that deeper structure. We have the clues, some of them extraordinarily precise and powerful, and we have the frameworks that the clues suggest, the holographic principle, the AD-SCFT correspondence, the emergence of spacetime from entanglement. We do not yet have the complete theory that assembles these frameworks into a consistent and explicit description of quantum gravity. That theory is being built by physicists working at the intersection of string theory and quantum information, and general relativity and quantum field theory, and its construction is one of the most active and productive areas of fundamental physics in the current era. While that construction is ongoing, the black holes continue doing what they do. The supermassive black hole at the center of the Milky Way continues processing the quantum information of everything that has fallen through its horizon over the galaxy's history, scrambling it at the maximum rate that physics permits, holding the ledger balanced while the balance remains unreadable. The stellar mass black holes scattered through the galaxy continue their slower evaporation, their hawking radiation so cold and so faint that it is utterly unmeasurable by current or foreseeable instruments, but real and continuous and eventually consequential. The binary black holes that LIGO and Virgo continue to detect continue their inspiral and merger, each event releasing a burst of gravitational energy and producing a new, more massive black hole that will outlast every star in the galaxy. And somewhere in the universe, right now, a massive star is crossing the threshold at which neutron degeneracy pressure can no longer support the iron core. The collapse is beginning, and in the next fraction of a second, a new event horizon will form. A new causal boundary will come into existence, enclosing a region of spacetime from which nothing will emerge, processing the quantum information of the collapsing star at the maximum scrambling rate, beginning the long and patient wait before Hawking radiation returns that information, transformed beyond recognition, to the universe. The event is happening, or has happened, or will happen on the light cone of our current position. Somewhere in the 13.8 billion light-year sphere of the observable universe, new black holes are forming on a timescale of 1 to several per second. Each one a new surface that has never been crossed outward. Each one a new information processor beginning its work. Each one a new window into the nature of spacetime at its most fundamental level. The night sky contains the light from galaxies that have supermassive black holes at their centers, black holes whose jets and accretion disks make the whole galaxy shine at distances of billions of light years. The night sky contains the light from stars that will one day collapse into black holes, whose futures include the formation of an event horizon that will remain uncrossed in the outward direction until the universe has aged past all comprehension. The night sky is full of black holes, visible by their effects and by the light they bend and the matter they consume and the gravitational waves they produce, absent in the most direct sense of the word absent, taking everything in and returning nothing on any timescale relevant to the stelliferous era. And yet the ledger is balanced. The physics requires it. The quantum information that has been absorbed into every black hole in the universe is not lost. It is held, processed, scrambled, held again, and eventually returned, in a form that no observer in the stelliferous era will ever be able to read, on timescales that make the stelliferous era itself look brief. The universe keeps its accounts. Nothing is permanently lost. Everything that has ever entered a black hole is still there, in the quantum state of the horizon, in the correlations of the early Hawking radiation, in the entanglement structure of the evaporation process, waiting in the patient darkness of the event horizon for a future that is, by any measure we can apply, effectively infinite. That patience, that completeness, that absolute conservation of what has been, is the deepest thing the study of black holes has revealed. Not the violence of the accretion, not the drama of the merger, not the strangeness of the singularity, not even the wonder of the Hawking temperature. Those are all real and remarkable, but the deepest thing is the conservation. The fact that the universe does not forget. That every quantum state of every particle that has ever crossed every event horizon in the history of the cosmos is still encoded, somewhere, in the quantum state of the universe, waiting to be returned in the fullness of an unimaginable time. The universe does not forget, it only waits. Thank you for spending this night with the objects from which nothing returns, and with the physics that says everything returns eventually. This is Dusk and Discovery. If these are the nights you want, subscribe and come back. The universe will be here. Sleep well.